Greetings, my name is Reza Tasuji. I'm a PhD student in computer science at Virginia Tech, working with Dr. Gratchen and Dr. Knapp as my advisors. My area of research is affective computing, mainly focusing on analyzing psychophysiological responses using deep learning models. This video covers our paper with the title Exploring the Impact of Labeling on Psychophysiological Data Analysis. So without further ado, let's start with our introduction section. So before we start, let's go through some definitions. One of the goals in human-computer interaction, HCI, is to reduce the complexity of interaction between user and computer. One approach is to include affective computing in our design to achieve this goal. With this approach, the goal is to decrease the amount of cognitive load and create more natural behavior between user and computer. But what is affective computing? In short, affective computing includes different approaches that consider users' emotion as input for the system. Okay, good, but now what is emotion? It's one of those terms that we all know what it is. Still, it's hard to describe. But in general, it is an umbrella term for all of our behavioral, expressive, cognitive, and physiological changes that occur. One challenging aspect of affective computing is that our feelings and emotions are subjective. So when we want to use emotion as an input for a system, there will always be a doubt about how practical such approaches can be. So researchers need to define a label that they assume can be caused by the stimulus. For example, there's a sad song and a happy song. In this case, the song, which is the stimulus, is assumed to cause sadness or happiness. So researchers with typological thinking assume that there can be a fingerprint that can be found and might be universal. On the other hand, researchers with populational thinking believe variation is a norm and regularities in population arise from individual activities. Still, the correctness of label depends on social beliefs. Under a similar context, we expect a commonality in behavior. A person needs to be sad when grieving or happy when they are excited. Now, the question is, how can we analyze such social beliefs? This brings us to our motivation. In recent years, deep learning methods replaced traditional machine learning approaches due to their ability to learn automatically features from data. To evaluate the correctness of such models and explore their practicability, we need to know the ground truth. And as we mentioned, in the world of affective computing, the ground truth is debatable. So it brings us to our motivation to explore the impact of labeling on psychophysiological responses. With this, let's define our research question. What analytical approach can explore the impact of labeling in psychophysiological responses? The goal of exploring this problem is to develop a model that uses psychophysiological responses as an input and can be practical. By practical, I mean it can be used by many people with an acceptable outcome. The requirements for exploring this problem are, first, is to have access to a large number of psychophysiological responses to a stimuli. Then we explore multiple deep learning architecture, not to predict the outcome, but explore if the network can classify such labeling. So to some extent, the goal of our models is not to predict, but to help us understand the psychophysiological data and the label associated with them. We propose the following data analytic approach. The following slides cover each block in more detail, starting with labels. The basis of our approach is to explore the commonality of the labels defined in big psychophysiological responses data. We consider labels as null hypotheses that can or cannot be rejected. Our approach is a discriminative binary approach that compares only two labels. For example, the model's input during training can be a response to a sad song versus a happy song, or male versus female responses to the same stimuli, or responses to the same stimuli in two different geographical locations. The reason for the binary approach is that it can help us to gradually include responses that are not significantly different from each other and then compare them to a larger population. Although such a binary approach is simple, it can be practical. At least it is possible to distinguish between two different responses. One of the requirements for using deep learning methods is to have access to a large number of data to avoid overfitting and to regularize the result. After defining the binary labels and querying them from the database, the next step is to feed the data into the binary classifier to train. At this step, we can add different deep learning architectures, such as feed-forward network, recurrent network, or generative networks into the workflow. But there is a problem with this approach, which is after training the model, no matter what we feed into the model, it will be classified as one of the two labels that we define. For example, let's say we train our model to separate a picture of a cat from a dog, a binary classifier, a cat versus a dog. We train our model using pictures of cats and dogs. After training, if we feed a picture of, let's say, a zebra into our model, it will be predicted as a cat or a dog. Besides a binary classifier, a clustering approach can help us better understand the outcome. After the training phase, the result from the classifier and clustering is presented as a confusion matrix during the testing phase. The confusion matrix holds the information about correctly classified responses known as true positive and true negative, and responses that are falsely classified, false positive and false negative. So within each confusion matrix, we can analyze 4 groups further to understand what is causing such results. We divide our analysis into 3 categories. Report analysis focuses on analyzing pre and post questionnaires between groups. ANOVA can be used at this step to see if there is any significant differences between groups. Response analysis includes methods for analyzing psychophysiological responses within each group and comparing the differences between groups. Then we have label analysis to compare the result from the classifier and clustering. And also here we explore what the model sees as features that cause such classification. Class activation map, CAM, is one of the approaches that can help us explore what the network sees as a feature. Now, about the database that we use in our study, here are some of the databases that contain psychophysiological responses. Because most of these databases are collected in a control environment to provide a good quality response, the number of participants is very few to be used for deep learning models and cannot be generalized. As far as we know, EmotionAware is the only database that contains over 60,000 psychophysiological responses to audio stimuli. The main problem with EmotionAware is that it is collected in the wild without any control, which causes to have lots of poor quality signals. About the deep learning network that we use in our study, for classification, we use the CNN, convolution neural network model with skip connection. The input of the model is electrodermal activity responses. Recent studies suggest that converting a 1D time series signal to a 2D image can improve performance. So we try to explore this to check if the 2 models provide close results. The input for one model is a 1D time series data, while the input for another model is the converted time series signal to a gray image using a Gramian angular field approach. For clustering, we use a spectral clustering using dynamic time warping as an affinity matrix. As for a binary label, we selected EDA responses caused by listening to a pink noise versus listening to a song. Our null hypothesis is that the differences between the 2 responses are significant enough to be classified with acceptable accuracy because pink noise does not have any musical structure. Now, before jumping into the results, these are the definitions used in the study. True positive, the input is labeled as noise and the classifier predicted it correctly. We have true negative, the input is labeled as a song and the classifier predicted it correctly. And based on this, we have our false negative and false positive. As mentioned, there are 3 models to explore the impact of such labeling on the result. ResNet model using time series, ResNet model using encoded time series at a 2D image, and our spectral clustering using dynamic time warping to generate affinity matrix. Here you can see the result for 5 songs. In all cases for classification, both 1D and 2D input, the values for true positive and true negative are significantly higher than false positive and false negative, which can indicate there might be something significant about listening to pink noise that can cause such a detectable response. Also, we can see the encoded time series improve the prediction as we expected. And here you can see the result for all 18 songs. To better understand what the network sees as features, we randomly selected 50 1D EDA responses to pink noise and a song to generate class activation map. We can interpret the brighter areas as patterns that the classifier sees to predict the label. We can see the beginning and the end of the pink noise responses are the main features that the network sees to define the signal as a response to pink noise. At the beginning of a response, such a pattern can be expected from pink noise, as a sudden noise can be interpreted as a startled response. This brings us to our conclusion that by having access to a large number of psychophysiological responses to different stimuli, we can explore which binary label can be generalized. By defining binary labels as null hypotheses, we can explore the commonality of such labels in the database, which leads to rejecting or keeping our null hypothesis. Having access to a large number of psychophysiological responses is crucial for this approach. For future work, other deep learning architectures such as long short-term memory also needs to be included. We use a spectral clustering as suggested in Wei Hong's paper. It is preferred to use clustering approaches that leverage deep learning architectures. Deep embedded clustering, DC, is such as an example. Also, variation or autoencoder is a generative model that can be used for clustering purposes. We are currently working on including more models and exploring more binary labels. And that was our study. Thank you very much for taking the time to watch this video. If you have any question, please do not hesitate to contact me. My email address is rtasuji@vt.edu. You can see it in the screen. I'm looking forward to it, and thank you.